All right, let's get restarted here. So we're going to start putting together kind of the last couple of days of work. So we're looking at kind of the relationship between the acid dissociation constant, Ka, the hydronium concentration, and pH. And we're going to look at another value here called percent ionization. Percent ionization gets us to a measurement of acid strength based upon how much of the original concentration of the weak acid broke apart. And so we can measure it as the concentration that ionized compared to the original concentration. And what that means in terms of values is we're looking at the concentration of the hydronium ion at equilibrium over the concentration of the acid that we started with. And that ratio of values times 100% will give us the percent ionization. Percent ionization also is another indicator of acid strength. So between Ka and our already known notions of acid strength based on strong acid, weak acid, percent ionization is another way that we can kind of characterize. So let's do an example here. Calculate the Ka of a 0.085 molar solution of phenylacetic acid if the solution has a pH of 2.68. Also determine the percent ionization. So phenylacetic acid is an organic acid. And we could go into the values here and look up what the actual chemical formula is for phenylacetic acid. But reality here is that it's not important. What's really important is we need to just set up a generic equilibrium here to solve this problem. So I'm just going to call phenylacetic acid H-phen. That's the hydrogen ion, the thing that is going to be acidic, plus everything else that makes up phenylacetic acid. That stuff reacts with water to make hydronium ion and that conjugate base, phenylacetate. Our initial concentration is 0.085 molar phenylacetic acid. Since water is a pure liquid, we don't care about its concentration at all. And we can safely assume that there is no concentration of either of these two products at the initial moment of reaction. Setting up the rest of our ice table, we know we're going to lose some amount of acid. Don't care about the water still. We're going to gain some amount of hydronium, gain some amount of hydroxide. And again, the good news in these kinds of equilibria, all of our X's are ones. So in some ways, the equilibria that we just took that quiz over are a little bit more difficult than these, just because when we're talking about these acids interacting with water, everything's 1 to 1 to 1 to 1 to 1. So at equilibrium, I'm going to have 0.085 minus X for phenylacetic acid. Still don't care about water. Hydronium is going to be X. phenylacetate is going to be X also. Now, the important piece of information here that we're given is that the pH of this acid is 2.68, which means we know from the kinds of problems that we were just doing in the previous set that the hydronium concentration would be equal to the antilog of that pH, 10 to the negative 2.68. Since I have 2 decimal places, I'm talking about 2 sig figs here. 2 sig figs will give me 2.1 times 10 to the negative third molar as the concentration of the hydronium ion. That's also going to be my value of X here. So substituting in for X, I'm going to have 2.1 times 10 to the negative third molar for hydronium, 2.1 times 10 to the negative third molar for the conjugate base, 0.085 minus 2.1 times 10 to the negative third is going to give me 0.083 for the phenylacetate, or excuse me, phenylacetic acid. So to determine the value of Ka, I would take the concentration of my products divided by the concentration of my reactants. So 2.1 times 10 to the negative third times 2.1 times 10 to the negative third divided by 0.083 to 2 significant figures. I would get 5.3 times 10 to the negative fifth. Which should make sense. This is still quite reactant favored, even though the pH is pretty good. 2.86 is acidic. We can see from the concentration values here, there is more reactant than there are products. So we would expect a low value for our Ka. Now to do percent ionization, I need the concentration of hydronium at equilibrium over the concentration of the weak acid initially times 100%. So we're looking at 2.1 times 10 to the negative third molar over 0.085 molar times 100%. To 2 significant figures, we're talking about 2.5%. So for all of that, we're only seeing 2.5% of those molecules actually breaking apart. That means that 97.5% of the molecules stayed as molecules for phenylacetic acid. Now, if you remember from Chem 105, I gave you a general rule of thumb that said about 5% of weak acid molecules ionize. Well, in a lot of ways, that's going to be a gross underrepresentation. We're actually going to, or excuse me, a gross overrepresentation. We're going to see most weak acids fall short of that line. Now, a lot of factors do go into this. What is the concentration of the acid? What is the Ka? Those do make a significant difference. But overall, 5% usually is where we kind of top out, unless we're dealing with more robust acids or acids at particularly low concentrations. Because what we'll find is that at lower concentrations, that percent ionization value will go up just because it's not going to take as much to do so. All right, questions about this example? All right, I want you to start trying one here then. pH of a 1 molar solution of formic acid is 1.88. Determine the percent ionization of the formic acid and its Ka value. So I'll give you a few minutes. You're going to have to sketch out an ice table and kind of take it from there. See what you can do. We'll come back in a few. All right, let's see how we're doing. So if you had trouble getting started, you'll want to look at the setups here as far as the ice table is concerned and kind of what you needed to do. So you had to set up your ice table. The formic acid was going to be 1 molar initially, everything else zeros. So you should have had X at equilibrium for the hydronium, X for the formate ion, 1 minus X for the formic acid. The other thing that you needed to do, the pH of the solution was 1.88. So you needed to take the antilog of that pH to get yourself the hydronium ion concentration. That would be the concentration at equilibrium. So this is our X value. So that means that at equilibrium, we have concentrations of 1.3 times 10 to the negative second for both of our products. And 1 minus 1.3 times 10 to the negative second would be 0.99 molar for the formic acid. So for the percent ionization, the first question here, we would want the concentration of hydronium at equilibrium. So 1.3 times 10 to the negative second over the initial concentration, 1 times 100%. So that would be 1.3 times 10 to the negative second times 100, which would be 1.3%. For the Ka value, we got to take those 1.3 times 10 to the second negative second values. So that'd be quantity squared divided by 0.99. Our Ka value 1.3 times 10 to the negative second squared divided by 0.99 will give you 1.7 times 10 to the negative fourth. Now, again, what's interesting here is if I compare this example to the previous example, I will see that my Ka value is better. Again, compare it to what we were doing here. Our Ka value was 5 times 10 to the negative fifth. Here it is 1.7 times 10 to the negative fourth. But the percent ionization for that weaker acid was better, 2.5% versus 1.3%. And so this is what I was saying at the time, is that percent ionization value is not just a matter of the strength of the acid. It factors into that, but if we have a more concentrated value of acid, a more concentrated initial concentration, we're going to find that the percent ionization is going to be lower generally. And that's going to play a significant factor as well. So we can't just go based solely off of one piece of data if I'm trying to figure out acid strength from percent ionizations. I've got to look at concentration values as well. If they're the same concentration, then you can look at the percent ionizations. If not, then it's not really a good apples to apples comparison. Any questions with this example? All right, let's take a look at another one here. We have saccharin, which is a sugar substitute as a weak acid, has a pKa of 2.32. Determine the pH of a 0.1 molar solution of saccharin. Now, again, if I don't know the chemical formula of the substance, it really doesn't matter. I can create a general equation that will do basically what I need it to do. So I've got whatever that acidic component of saccharin is reacting with water to make hydronium, and whatever is left over from that saccharin molecule after the hydrogen ion is donated. Initial concentration, we have 0.10 molar saccharin. And nothing else. So our ice table setup is going to be unremarkably similar to what we have done in the past few examples. The difference this time is that we are not being given a pH value. So we're not working through this to find a Ka. Instead, we've been given a pKa value, and a pKa would be the same as every other thing that we've put under that P function. It's the negative logarithm of the Ka value. So if I do a little bit of algebraic maneuvering, negative pKa is equal to the log of Ka. Take the anti-log of both sides. 10 to the negative pKa is equal to the Ka. So 10 to the negative 2.32 is equal to the Ka value of this reaction, which means that Ka is equal to 4.8 times 10 to the negative third. Now what we have is something that a lot more closely resembles kind of that typical ice table calculation that we saw in chapter 14. .8 times 10 to the negative third is equal to x times x over 0.10 minus x. So if you apply the 5% approximation here, what you'll find is that these two values are 4.8% apart. That's not good enough for us. They're a little bit too close for comfort. So we're going to have to solve a quadratic out in this case. Not our favorite thing to do, but things could certainly be a lot worse than that. So if we carry that all the way through, x squared plus 4.8 times 10 to the negative third x minus 4.8 times 10 to the negative fourth is equal to 0. We can put that into our favorite equation solver. So A in this case is equal to 1. B in this case is positive 4.8 times 10 to the negative, or yes, 10 to the negative third. C in this case is negative 4.8 times 10 to the negative fourth. And we're going to get two roots as a possibility. One of them is negative, which makes no sense. Can't have a negative concentration. The other one, to two significant figures, would be 0.020. So that is the one that we will use. Since we are being asked for the pH of the solution, we need to know the hydronium concentration, which is X. So the pH is equal to the negative log of the hydronium concentration, which is 0.020. And 2 sig figs going into the log means 2 decimal places coming out. We get a pH here of 1.70. Now, there are a lot of ways that we could kind of double check ourselves. We could go back and plug all of these values in and see if we get our Ka value out. So if I did 0.02 squared divided by 0.08, I get 5 times 10 to the negative third, which is within rounding of the Ka value that we determined from the, so chances are pretty good we're on solid footing as far as the calculations are concerned. All right, any questions with this example? All right, so here's another question for you then. If I have a solution of hydrofluoric acid, Ka for hydrofluoric acid is 6.8 times 10 to the negative fourth, and it has a pH of 3.65. What was its initial concentration? So you have to do a little bit of backtracking here. Can you figure out the initial concentration? Still going to need to use an ice table, but you're going to use the ice table just a little bit differently. So interested to see what you come up with. We'll walk you through it in a couple of minutes. All right, so this type of problem can be tricky because it feels like, and I'll show you the ice table that I started with. It kind of feels like we have way too many unknowns in our ice table. After all, we don't know our ending concentrations of the hydronium or the fluoride, and we don't really know anything about our HF either. So how do I piece this together to give us a Ka value of 6.8 times 10 to the negative fourth? Well, the thing that we have to look at is that pH value of 3.65 does give us some information. It does actually solve one of those variables there. And so one of the things I did is I gave my variable for the initial concentration a different letter, just so that it didn't get lost in the wash with all the other X's. But if I took that pH value 3.65, took the anti-log of it, I got 2.2 times 10 to the negative fourth as the concentration of the hydronium. So that would be this value X here. And this X here. And part of this value for the equilibrium, 2.2 times 10 to the negative fourth on it as well. Now that doesn't fully solve the problem for me, but it does make things a little bit easier because now I can use this Ka expression. Ka was going to be equal to the concentration of the hydronium times the fluoride over HF. And now I have values for all of those other than HF. So 6.8 times 10 to the negative fourth is equal to 2.2 times 10 to the negative fourth squared. Now, for ease of algebra, I'm just going to put concentration of HF in that denominator so that I don't have to do an expansion and everything else. So I'm just going to make my life a little bit easier here. I know I'm going to have to do something with that m minus 2.2 times 10 to the negative fourth. I'm going to put that to the side for a minute, though. So algebraically, let's switch the Ka and the HF. HF is equal to 2.2 times 10 to the negative fourth squared divided by 6.8 times 10 to the negative fourth, which would give two significant figures, 7.1 times 10 to the negative fifth molar as the concentration of HF. Now, I know that this value is equal to whatever my initial value was, minus 2.2 times 10 to the negative fourth. Algebra says I just need to add 2.2 times 10 to the negative fourth to both sides. My initial concentration of hydrogen fluoride, hydrofluoric acid, would be equal to 2.2 times 10 to the negative fourth plus 7.1 times 10 to the negative fifth, which would give me 2.9 times 10 to the negative fourth molar. So again, what we can see here is another, our Ka value is not particularly large, but you can see we got a lot of ionization out of this one. We weren't asked, but 2.2 times 10 to the negative fourth divided by 2.9 times 10 to the negative fourth is 76% ionization. Like I said, concentration is a big contributing factor to percent ionization. Right. Any questions about this example before we take a quick look at bases and wrap it up for the day? So really, the only thing that we need to talk about with regard to bases is just how similar the whole thing is to acids. Really, all that is changing is that we're focusing on hydroxide instead of hydronium, and we're looking at a conjugate acid instead of a conjugate base. Aside from that, the equilibrium is basically the same. But because we are dealing with basic particles and equilibria characteristics, we're going to call this one Kb instead of Ka, because we're talking about a base equilibrium instead of an acid equilibrium. But like I said, other than that, look at the structure. It's almost identical. Only difference is how is the reaction acting. Instead of having an acid with water acting as a base, I have base with water acting as an acid. The conjugate acid is the conjugate of the base. The conjugate base is the hydroxide that's left over after the water gives up its proton. So all we really are going to end up doing is tilting our perspective and focusing on hydroxide and POH instead of hydronium and pH. So really what it just ends up is we end up having to do one extra step, because No one actually measures POH. We measure pH. And so we'll have to do one more conversion to turn the POH into pH or the pH into POH so that we can do the rest of the calculations. Similar to what we had with KAs, there is a table of KB values. You can find it in your appendix tables. You can also find it here in the lecture packet. If you go past all of this thermodynamic data, what you'll see is starting here on page 22 of this document, here are all of your Ka values for all of your different acids. And then here are your Kb values for all of your different bases. Now, this part we've already covered as well, just the idea that most of the bases that we are going to encounter are either going to be hydroxide salts, which for the most part we'll either consider to be strong bases, or in the case of the ones that are weak, we'll look at their Kb values and adjust accordingly, or they're going to be nitrogen containing organic compounds, where again, that nitrogen with that lone pair of electrons on it just goes out and snaps a hydrogen off of something, water usually, to form the two conjugates. Now, there is a third place where we can see it, and that is when we have conjugate bases of weak acids. Those conjugate bases of those weak acids can be aggressive toward water, can act in the same kind of way, and create basic solutions as a result. We'll get more into that tomorrow when we start to look at trying to evaluate and predict the pH of a salt just by looking at the chemical formula. All right, let's do one exercise and then we'll cut out here for lunch. Calculate the pH and the concentration of hydroxide in a 0.15 molar solution of aniline. Aniline is C6H5NH2. Its Kb value is 4.0 times 10 to the negative 10th. So we know the value of, we know the formula of aniline here. It's not super important. We could always fake it if we had to. But since we have it, we'll go ahead and use it. C6H5NH2 reacting with water as a base means it's going to add an H plus, C6H5NH3 plus, and that water is going to, after adding its H plus, be left with just OH minus. Initial concentration for the aniline was 0.15 molar. Don't care about the water's concentration. Initial concentration of the anilinium and the hydroxide ion would be both 0. Our ice table takes on some familiar territory. So again, it can be kind of boggling here how often this equilibrium ice table ends up looking exactly the same as the last one that you did, and exactly the same as the one that you did before that and the one that you did before that. There is some monotony in there. But it's actually, if you want to think of monotony as a good thing, the fact that it is so predictable does mean that once we kind of get used to doing it, you can kind of just do it. So our equilibrium concentrations, 0.15 minus X for the aniline, X for the anilinium ion, X for the hydroxide ion. Setting up our equilibrium expression. Here is a prime example of the 5% rule in action. Our concentration 0.15 is leaps and bounds ahead of the KB value on the order of 10 to the negative 10th. So when we set up this equilibrium expression, 4 times 10 to the negative 10th is equal to x times x over 0.15 minus x, we can state with pretty good certainty that the aniline concentration is not going to change significantly. So that is going to condense this down to x squared over 0.15, which means we don't have to solve a quadratic anymore. 4 times 10 to the negative 10th multiplied by 0.15 gives us 6.0 times 10 to the negative 11th is equal to x squared. Take the square root of that. You get 7.7 times 10 to the negative 6th molar is equal to x, which is equal to the hydroxide concentration. So yes, you can subtract 0.15 minus 7.7 times 10 to the negative 6th. You're going to get 0.1499999 which is basically the same thing. So what we're really interested in here, this concentration of hydroxide is going to allow us to calculate the pOH. pOH would be equal to 5.11 in this scenario. The pH would be equal to 14 minus that, which would be 8.89. So this is pretty much the same kind of problem that we saw with the previous examples with the acids, only we've got that one extra conversion to make. And that's one of the reasons why you'll see in the homework tonight, there's going to be a good bit of those convert pH into pOH, convert hydrogen into hydroxide, convert all of them between each other, go laps around that rectangle. Because where we use that information is right here. When we have information about bases using acidic kinds of measurements or vice versa, we need to be able to quickly convert from one set to the other without making mistakes. And so that's where we will stop for today. There is a question, we'll lead with that question tomorrow after the exam. So last thing I need from you for today before you go to lunch is just give a little bit of quick feedback there. And then you are free to go to lunch. Once you do, we will reconvene at 1:15. So you've got a little bit more than an hour. And we will start with the group 2 activities. And then we'll come back into the classroom here and do some exam review after that. Enjoy your break.